putting the committee in a tricky position, because it's far-reaching, and I hope that this talk will clear up some of the questions and confusion. But I'm not sure.
I don't think that's quite the goal, though.
Committee is listening to you. Okay, that looks better.
It works. Isn't that amazing?
Okay,
I've
go
got
ahead.
to set up the mic. We're almost there. Oh, sorry for the noise. So how do I set that up? Here. Okay, I don't quite know how this is. So that's why I work with computers. I don't have to hold things. How does that work? Well, do you hear me?
Yeah.
Is the camera hearing me? Yeah, okay. The goal is not really to help the thing be less confusing, or to talk about, or to talk about the details of the proposal and how things are supposed to work from a language level, but rather to tackle a point that was not discussed a lot in public so far, which is how do we implement that. So that rather adds complexity, I guess, but it's orthogonal complexity for the most part. So I put together the slides with everything I could remember was interesting about the implementation. So I forgot things, that's necessary. So I just want to be clear that please interrupt me if you have any question, if you have any feature that you think, oh, that's hard, how do you do that? Do ask. If you know this part of the compiler and you think this is hard with linear types, do ask, because I forgot things. That's sure. I don't know which, because I forgot them. Okay, so okay, oh, that's working. I won't be assuming that you have read the entire proposal and you remember it, et cetera, but I'll be very, very, very brief on what I'm going to speak of. The gist of the proposal, the gist of linear Haskell as we wrote it, is that we put the linearity thing in the function types. Meaning it's a type of different kind of functions. There are linear functions and non-linear functions, and they apply to all kinds of types. The types themselves are not segregated, which is the case in many other papers that wrote about linearity. For instance, I don't know, integers can appear in linear functions and non-linear functions. As it happens, it's probably very important. It's what seems to be making the system quite simple in comparison with other systems. It's also linearity, not uniqueness. It's not particularly geared toward doing array updates in place. You can do it, but it requires further encoding. So the entire sort of meta definition is we define a type of linear function, and a linear function is defined as if the result is consumed exactly once, then the argument is also consumed exactly once. And that's all. And of course, as I'll remove this pointer, it's ugly. I mean, it almost goes without saying, but it's backwards compatible. And the reason why I'm mentioning that is because I'm changing things. I'm making some things more general, but it needs to be invisible for the users. Also, I lied. Yeah, it's pretty early for a lie. But anyway, what I really did is not adding a new type of functions, is I generalized that function with a new parameter that we call multiplicity. And this multiplicity can be several things. It can be omega to say it's a function like you used to, or it can be 1 to say it's a linear function, the lollipop arrow from earlier. Or it can be a variable to say that it's polymorphic in this. Or it can be a polynomial, because, yeah. It's required. You'll see next slide. And so the multiplicity is just formally needs to have a certain amount of laws verified for the system to work. It needs to verify semi-ring low. It needs to be ordered. It needs to have joins and things like this. I mean, it's not the entire set of laws, but it's some of them. And it really doesn't matter for today, except that there's a plus and a time, and a smaller than equal to. We'll see them again. So that's the entirety of the system that I will be presenting today. 2 rules. It's not quite complete, but it's fairly representative. What's happening here is that when we type application, or like a pair is the same, we cannot type the F and the U separately, and we put together their contexts so as to count whether things have been used several times or have been used in both. The question is, if I have a variable x, has it been used both in F and U, or just in F, or just in U, or in neither? And all of these are typed slightly differently. And the multiplicity in which a variable can be used is constrained by the lambda, and it's just symmetric with the multiplicity on the arrow that we showed on the previous slide. So yeah, that's it. But if you go and implement this, there's a very well-known problem about linear types. Oh yeah, there's also a multiplication here. So just you quite see first that this is where I'm using addition and multiplication. It's in the application taping rule. And they're all lifted to contexts, which technically make context modules of semi-ring, blah, blah, blah. Doesn't matter. But the point is this is the reason why we have these. It's just to be able to express this rule. But it's a hard rule to do. So imagine I read that bottom to top. I have f of u and it's supposed to be of type t. How do I check that? Well, so I've got to figure a gamma and a delta so that my context is gamma plus pi delta. Oh my, I just dropped the mic. Excellent. I really don't know how to use this. I'll hold it in my hand. I don't know. Someone tell me otherwise. So you do have to figure, you have to split this context. And context splitting is amazingly hard. So what do? We don't do it. So we changed the rules for the purpose of type checking with something that we hope is equivalent, a bit more than hope, so that it's more algorithmic. So we take away all the multiplicities from the gammas and the deltas and so on and so forth, and we also take away splitting. So we have a single gamma with that multiplicity in it, but we add a new thing, the U here, or V, that I called a usage environment. It's a reported way in which the variable has been used. And in a type checking algorithm, we see that as an output. So instead of saying term to type to bool, or type checking algorithm will be something like term to type to maybe a usage environment. And then we don't have to do any splitting. We can still read that bottom to top, except that, wrong button, interesting. Except that the u plus pi times v here comes after. It's an output. And so this is much more algorithmic. And this introduces the smaller or equal thing too. This is introduced by the lambda. So because you have a lambda to type check, and so you type check the u inside. The u says, oh, I've used x with multiplicity rho. Great. Is rho compatible with pi? Yes. No. If not, it's not well typed. So what happens typically is I've used x twice, and lambda x was linear, so I have a constraint omega smaller than 1, and then the type checker says no. And that's pretty much it. So to implement this, we create a new type of multiplicity. It's got 1 in omega. It's got a 0 because it's useful, but it's hidden. It's just inside. It's got addition and multiplication formally, and then you can insert any type because that's how we add variables. They're just regular type variables. So they're inserted there. Light, no light. What happened? And so yeah, usually the type thing will be a variable. There's a bit of a complication is that there are two Haskells in this talk. Yes. Why do I need what? I was getting there. But thanks for the segue. One of the complications is that there are two Haskells in this talk. There's the linear Haskell, Haskell the language, and there's Haskell not necessarily linear, which is Haskell the implementation thingy, or the meta language. And the slightly different color is for Haskell the language here, and Haskell the meta language there. And the multiplicity is just a type that we use as a promoted kind to carry multiplicities as type variables. So a multiplicity variable is a type variable whose type is multiplicity. And mult is the internal thing that we use to represent multiplicities, yeah. There's just technical things, but it's probably not needed. It's just useful to be able to give a default values for things that are absent. It appears during type checking. Yes. It's just it's an artifact of the usage environment. The values, so the absent values from a usage environment are morally used 0 times. And if we want to use a fine width default or things like this within this environment, I use a 0 to represent this. It simplifies. It just simplifies doing things are pairwise smaller or equal. Yeah, there are other questions. I'll get there. Don't worry. So yeah, so I want to say I want to say U is smaller than V. That happens sometimes. So everything in U is smaller than everything in V. So I say, well, to take all pairs, and if an element is absent, put 0 and then check. That's the reason why there's a 0. Should probably not have put in the slide. It doesn't matter all that much, but it's just a technical thing that I've been using. It simplifies implementation. It's possible that 0 is an interesting multiplicity too, but it has its own complications, and it's further work. Yes.
Why there's inequality instead of equality?
Because this is a reported value, yeah? So if you say, okay, I can use x as many times as I want, and U says, oh, I've used x exactly once. Well, you pretty much have, if you say, no, that's not right. You could use it as many times as you wanted. That's not right. So this is the inequality this is what the inequality is for, yeah. So he says 1 is more than omega, so he says, oh, yeah, okay, right.
Is this a fine Haskell instead of linear Haskell?
It's linear.
Except for
You
omega.
can also use it always less than...
No, 0 is not smaller than 1 in that system.
0 is not smaller.
Right. So yeah, 0 and 1. The way I see them is I see them as sets in the power set of n. So sets of natural numbers, and 0 and 1 are the singleton 0 and 1, whereas omega is all of n, and then you use inclusion as your order. It's my intuition. Yeah, there was a question there.
So 2 is also greater than 1 and 3 is greater than 10.
No, they're incompatible. If I added 2, well, I mean, it depends what you mean by 2, but typically, if you want exactly 2, it would not be compatible with the 0 or 1, by definition.
So there is no 2 in those numbers in your, this is the right side, right? Where we have only one omega.
Yeah. Well, these one are you have 0 in that one, but we only have 0, 1, and omega in the implementation. But it won't report a 0 because it will just not report anything for x if it doesn't see it. But you can see that as it's the same as saying that x has been used 0 time, which is so for the type system for the surface language, 0 times is the same as omega, but in the implementation you can't quite make that confusion because you need 0 plus 1 equals 1, and omega plus 1 is equal to omega, of course. Yeah? No? Complicated? Sorry. Okay. Do you have a question, Ben? No? Was there any other question? No? Okay. Okay, great. So the implementation strategy is basically the bottom line. I created a new type called weighted because I have no imagination for names. And we used, at some point we called multiplicity weight because I have no imagination for names. And so a weighted A is an A together with a multiplicity. And then in a bunch of places I replace type by weighted type. And then I follow the type checker.
Why can you lift an arbitrary type into a multiplicity?
Sorry?
Why can you lift an arbitrary type into a multiplicity? A multi? Why is that not type R?
Sorry, what are you pointing at?
The multi.
The multi, yeah.
Yeah.
Takes a type. So syntactically, any type can be.
Variable.
It's usually a variable, yeah.
But not always.
Well, so currently it's anything that has type multiplicity. So you are allowed as a Haskell user to write a type family that goes to multiplicity. It probably doesn't do anything, and the type checker will just treat that as a black box. But it can be anything, and we can actually transform back and forth between mult and something of type multiplicity. So there's also a multiplication and addition that appear in types.
Okay.
Anyways, I was saying that basically you replace type by a pair of a type and a multiplicity. You follow the type checker, propagate the multiplicities, and you've mostly finished the implementation of the type checker. Which is not the end of the story, and the rest of the talk will be about the rest of the story, mostly. Just a couple of words still on the surface language. This also changes the funtype constructor in type to add a multiplicity as an argument, and the corresponding funtype con, which is the name of the arrow between parentheses, which with here I put a dot here to say that it has an extra argument, but it's not actual syntax. We don't actually have syntax for this yet. Propose will be very welcome, and so it has one extra argument than previously, than the regular arrow, and this extra argument is a multiplicity. And contrary to the runtime reps that I've figured on this slide, this is an argument that needs to be specified because it can't be inferred from the other arguments. Sorry? The runtime reps, they are from Richard. It's just to be able to make an arrow that works on something that is unlifted. So it represents the calling convention of your functions, if you wish. And you never see them on the arrow. They're just completely invisible arguments. I mean, you can see them, but it requires... I don't know if you can see them without changing something in the compiler and recompiling GHC, but it doesn't matter. The point is, they're really just here for technical reasons. Without the multiplicity is really meaningful. Because I mean, basically the runtime reps, they are parameters of the kind of the two normal arguments. Yeah. Read the paper on levity polymorphism and everything will become clear. Okay, I haven't even started. Which one? Funtycon? Yeah, so it's... yeah. Yeah, it's a type of kind multiplicity. Yeah, so... No, it's me writing nonsense. Yeah, so it's multiplicity to type, plus the to type, sorry, yeah.
So I was expecting it to be more than that type.
Not in the funtycon, because it's just something that happens in Haskell, the language. So it's a type of kind multiplicity. But when it's reified into a funty, then we reify the type into a mult. Yeah, that's that. And the reason why there's this mult type is usually because we're doing much more stuff with it than with runtime reps, and it's convenient to have it as a type, to carry it as a type without the compiler. Okay. So I'll go slightly over the time because we had many questions already, but I mean, not over the question time, I mean. So I'll try to be a bit swifter. So yes, we have to change core as well, and basically 2 reasons for that. There's the silly reason. Core uses type, the same type as the type checker, and I've changed type, so I need to change core. Haha. But there's a better reason, which is that at the end of the day, core is kind of simpler as a language, and has much fewer features, and there are features where we don't really know what making them linear would make, and we want to be able to say, okay, well, let's try them and see if core says okay. So that way, core will be linear too when this is all finished. So it has mainly 2 consequences. We have a mult argument that is stored within every id, and the Funko coercion constructor has also a coercion for the multiplicity argument. We change fun type, we need to say Funko as well. I'll come back to that, but before I do so and move on, I just want to say that there's a particularly interesting pain point there, is that because the Funkos, they're injective in a certain, well, the type constructors are injective, all these ones, we can, from a coercion, access the coercion arguments. It's called nth, I think, in the papers. And this nth is actually used within GHC with concrete numbers written in the code. And of course, you add arguments, it changes the numbers. It's fun. And yeah, Matthew is nodding because he suffered a lot through that. You know where they all are. Okay. You suffered previously. Okay. Yeah, so it's not horrible, but it's the sort of thing that suggests that we might have to do something to make it easier, especially since like a few other people want to add more arguments to functions. So yeah, go on.
So in the paper and the proposal, you make a big deal about the fact that multiplicities are on the function arrow and not on the types or kinds or arguments.
Yeah.
And yet now we have a multiplicity on IDs. Why?
ID is not a type. ID has a type, and this multiplicity, it's like in the first slide. You have multiplicities in the context. So it's just like x colon index p alpha is represented as x with inside it a p and an alpha.
But I thought that was the declarative specification was put on the column, but then in the actual type checker it wasn't there. It was in the output in the U and the V.
Yeah, in the type checker, yeah, but we still need to have it somewhere. I mean, it's for the lambdas. It's in core, yeah. So in core, we carry it just like we carry the type. Oh my god. We'll have to be very fast. So I wanted to speak about transformations a bit. This is one transformation that core likes to do, at least in the declarative version. It's a bit different to implement. So you can very easily annotate it with linearity annotation with multiplicities. But you have to be careful. You can't just commute things. You have to scale the multiplicities. And because I've got like 5 minutes until I have to give back the mic, I won't explain why. I'm sorry. But it doesn't actually work in all cases because there's this case where let commutes with one branch of with one branch of a case. And if you try to annotate that, there's absolutely no annotation that will ever make that work if the pi and the row are both 1. It will just not type check. So we had to come up with a clever solution where the lets are typed slightly differently, and we annotate the x here not with a multiplicity, but with a usage environment that will be released when the variable is used. So the lets and the join points and so on and so forth, they are typed a bit differently than they would be in a normal programming language. I wanted to spend some time on it. I don't have time. I'm sorry. Let's move on. I said I was going back to coercions. So there's one of the rules in core to core is that if I have a coercion function applied to something, I can transform the coercion into a coercion to the result and a coercion to the argument, apply them both, and so that I can reduce the function, and it's much better. But it doesn't always work because, oh my God, we forgot the multiplicity thing. This is terrible, terrible, terrible. And of course, it's really bad because if the multiplicity thing is a non-safe coerce axiom, then it will just yield untyped type code. This may or may not have happened in practice. Anyway, so what I do currently is that I check that the multiplicity argument is refl, and otherwise I don't do the push. And it usually is refl. I mean, there might be a better way to do it, but it's sort of it's the safe things I've done so far, and there will be some analysis to see if it breaks things. Hope not. I'm very, very near the end of my slides. I just wanted to say that one interesting change is that all data constructors have wrappers now, or pretty much all, where before some were considered too simple to have a wrapper. And the reason is that we add a magic multiplicity argument on some things for backwards compatibility reasons. See, this is coming back. I was right to write it down. And yeah, okay. I leave it here. Do I have anything to say? Okay. So I just want to say that here are a few links. The slides are already linked from the program, so you can go there and fetch all these links. The first one is where I've been implementing that in Mathieu, mostly Mathieu really. And the second one is a page describing the implementation on the wiki. And finally, the proposal itself. I'm leaving that so that you can read if you want in the next few seconds. And that will be all because my time is quite up. Yes, it is.
Right, because there were